Anyway, I had a couple of requests on reviewing certain things, so I'm going to do a few. I just picked a few examples that I'll talk about, but if in the meantime you think of anything else you want to ask, then ask at any point. Okay? So first, here's kind of a famous example that I wanted to go through anyway, which is good review of geometric distribution and expectations. Then we will talk more about the universality of the uniforms, since that's the number one request. Okay, but first let's do a problem called the coupon collector. I think a couple of the sections did this problem or something similar, but not all of them, definitely. This is a really good example. It happens to be very useful in a lot of cases. I think of it as the toy collector problem, because I don't collect coupons. Well, I don't really collect toys either, but I'd rather collect toys than coupons. The problem is that you have a certain number of different types of toys, and you want to collect a full set. And it's like one of these like Happy Meal type of things where, you know, you buy a Happy Meal at McDonald's or whatever, and you get a random toy, and you want the full set, right? That's the problem. The problem is, on average, how long will it take you to collect the full set, okay? So we have a certain number of toys, let's say n toy types. I say type just because to distinguish between the individual toys, you might get 7 of the same toy, right? But I mean 7 of the same type, but 7 physical objects. So there are n types, and we'll assume that they're equally likely. Now in practice, they probably will make one really hard to find, so that then people go berserk, you know, going on eBay and stuff trying to track down the one hard one. But we'll assume right now they're equally likely. Problem gets very, very messy if they're not equally likely. Like really, really tedious, long calculations you go on for pages. So it's not something it's not something you would need to worry about for an exam in this course, because the problems that you will have to deal with or you'll have to deal with should have very short, nice solutions. And it gets really nasty if the probabilities are unequal. But in this case, it works out really nicely. So the question is, find the expected time to collect a full set, where time is just measured discretely in terms of how many toys you need to buy, right? Expected time, i.e. number of toys, until you have a complete set. And if you think of breaking up this random variable into smaller random variables, then it's easy to think about how to do this. So if we call this t for time and t for toys, we want to know t is the number of toys that we need to collect to get a full set. Let's think of just breaking down t into components. So it's t1 plus t2 plus blah, blah, blah plus tn, where t1 equals time until first new toy. By new, I mean a toy that we didn't already have. Well, that's actually equal to 1, because the first one you get, that's your first toy, and you didn't already have it, obviously. Okay? So that one, t1 is actually just a constant, always equal to 1. Now, t2, after you've collected your first toy, if you're unlucky, the second toy is the same as the first toy. But most of the time, you get something new on the second try, okay? So t2 is the additional time until your second new toy. So new just means one you didn't already collect earlier in the process. So additional time until second new toy. And then t3 is same thing until the third, and so on. So additional time after the second. That is, you collect till you get your second toy, collect till you get the third, and keep going like that until you have all of them. So all the way up to tn, okay? Then notice that T1 is just equal to 1. But T2, let's think about T2. So we have one, there are n different toy types, and we have one out of the n. So there's an n minus 1 over n chance that the next one is going to be something new, right? So we would consider that a success. So the success probably is n minus 1 over n. On the other hand, with probably 1 over n, we get a failure in the sense of collecting a toy we already had, and then it's the same problem again. So therefore, T2 minus 1 is geometric with probability of success n minus 1 over n. The minus 1 is just because of the convention about the geometric, that we're taking the convention that the geometric starts at 0. But of course, you need at least one more new toy, so I'm subtracting off that one. And in general, Tj minus 1 is going to be geometric. So Tj, we're trying to get the jth toy, right? That means that we already have collected j minus 1 toys. So it's going to be n minus the number we've already collected, which is j minus 1. So they're all geometrics. Then we can immediately write down the answer. In this case, these t's are independent, but linearity would hold even if these were dependent. Here they're independent because, right, it's just like how long does it take you to get your second new toy, but that has nothing to do with telling you how the additional time, right? But even if they were not independent, it would still be true that E of t equals the sum, E of t1 plus E of t2 plus E of tn. And just to simplify that, write out what that is. So that's E of t equals, so E of t1 is just 1. E of t2, well, we talked about the fact that if you have a geometric starting out at 1, then the mean is 1 over p, because that's q over p plus 1, because we're adding back the 1. So the next one is just going to be the reciprocal of this, which is n over n minus 1. And then the next one is going to be n over n minus 2, and so on. And then for the last term, that means that we have n minus 1 out of the n types. Then our probability of success is only 1 over n, right? So for the last one, it's n, which let's just write this as n over 1. Then we can factor out n. And so this is really just n times, and I'll reverse the order of terms just to make it look nicer. It's n times 1/2, 1 plus 1/2 plus 1/3 plus blah, 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 plus 1 over n. So that's called the nth harmonic sum, right? That looks like the harmonic series. This is approximately n log n for large n. That's just a useful fact about the harmonic series, that we can approximate it as logarithmic. But, you know, and just in general, for a midterm and homework and stuff, you should give exact answers unless you're asked for an approximation. So this would be the exact answer, but this would be a handy approximation for large n. So anyway, so we just used linearity and geometrics here, and then, you know, sounds like it could have been a hard problem, but as soon as you break it up into pieces like that, use linearity, then it becomes an easy problem. Okay, so let's talk a little more about the universality stuff, which there's always questions about. So I just want to draw a little picture and do a quick example to show more about what's going on with that. So here's a picture. So we're talking in the continuous case. So we have an x and f of x. So we're just imagine drawing a CDF. And remember, CDFs, you know, they have to be increasing and right continuous. But for universality, we're assuming that it's strictly increasing and it's continuous. So just draw some kind of CDF. Maybe it looks like that, and you know, either it hits 1 and then it would stay 1 forever, or it just asymptotically approaches 1. Either way is fine. But just to have like a picture in mind of what's universality really saying, what it says is, for example, what if we chose a random, so this is lowercase x here, this is just the x-axis, okay? But what if we chose a point on the x-axis randomly, okay? So the question is, why, basically, let x be distributed according to f. So x is the random variable, f is this curve, this CDF, okay? And the claim is that when you plug x, this is 1/2 of the universality. Remember, we talked about two parts, which are equivalent, so just talk about one of them right now. We said that if we plug x into its own CDF, we'll get a uniform. So I just want to explain using this picture why is that true. I think the easiest way to think of it is just to make it a little bit more concrete and pick a certain number here. Let's say, let's pick a number on the vertical. So here's 1, and maybe it hits 1, and then it would stay at 1 forever. Okay. Now let's pick some other number on the vertical axis. Let's say here is 1/3. So I just picked a y value of 1/3. Okay. And suppose that I ask the question. And so let's call this point here x sub 0. So x0 is the point such that f of x0 equals 1/3, right? That's the, just inverse of a function. Okay, so in other words, I'm just saying, I'm just making up, for some reason it looks really abstract at first, but I found that if I just make up a number like 1/3, it's easier to see what's going on. So you could have chosen any number between 0 and 1, but I picked 1/3. Okay, so I assumed that f of x0 equals 1/3. Now, I want to know what's the probability that f of capital X, that's a random variable, right? Because we're plugging this random variable into its own CDF. Okay, we want to know what's the probability that this is less than or equal to 1/3, where, so the interpretation of this f of capital X is we first pick a random value on the x-axis according to this distribution, right? This distribution is telling us how do we select the random x value, and then we compute the corresponding y value, which is f of x, right? So that's how you compute f of x. But notice that's true exactly. So I'm picking a random point here, somewhere on this x-axis, and I'm saying, when is it true that the y value is less than or equal to 1/3? Well, that's the same thing as saying that the x value has to be between here and here, right? Because if x were to the right, and I go up here, it's bigger than 1/3, and I said less than or equal to 1/3, okay? So that's the exact same thing as saying x is less than or equal to this x0, but by definition of the CDF, that's f of x0 equals 1/3. And there was nothing special about 1/3 here. You could do this for whatever number you want between 0 and 1. That's the uniform distribution. Right? The uniform distribution is saying that probability is proportional to length. And for the uniform 0, 1, probability is length within that interval 0 to 1. So that's what we just verified, that 1/3 became 1/3. Okay? So all this is saying is that the claim is that f of x is uniform between 0 and 1. And if you do the same calculation with any number here instead of 1/3, any number between 0 and 1, same thing holds. So that's what it's saying geometrically. Okay, we're just relating, random point on the x-axis to getting a random value vertically between 0 and 1. Okay, and as a quick example of how you might use that, suppose you wanted to simulate from the logistic distribution. We haven't defined the logistic distribution yet, but I'll just tell you what it is right now. The logistic distribution, which is another important distribution in statistics, that it's used in what's called logistic regression, for example, which is a very, very, very widely used method in economics and statistics and elsewhere. It's based on the logistic distribution, which has the following CDF. F of x equals e to the x over 1 plus e to the x. This is for all real x. For practice with CDFs, you can verify that this is a valid CDF. Right? There's three properties. It's continuous, increasing, and so on. You should check for yourself that this function I wrote down does have the properties of a CDF. So that's a valid CDF, but that doesn't tell us how we could ever simulate random variables that have that CDF. And if we wanted to do that, an easy way to do it would be let U be uniform 0, 1, which is easy to simulate, and then consider just doing F inverse of U. So if you set this thing equal to U, and then this is U in terms of X, but solve for X in terms of U, just by doing the inverse, just a little bit of algebra to get the inverse, what you'll get is this function log of U over 1 minus U. So that's just the inverse evaluated at U. Just do the algebra, compute the inverse of this, and that's what you'll get. That's another, that would be interpreted as the log of the odds, basically, if you think of this. If U were just a probability between 0 and 1, that would be the log of the odds. But in this case, U is a random variable, so we plugged it into its inverse CDF, and then that would be logistic. So if you just computed this thing, then you would have a random draw from the logistic distribution. Now, if you wanted, you can check that that's true just by taking this thing and just compute directly its CDF, use the definition of CDF, and you'll get this. But it's easier to recognize, that's really why it's working. Okay, so are there more questions that you've thought of since before? I have a few more examples that I thought of and things to talk about. But anyway, let me know if you think of any other questions. I wanted to do something more with symmetry and linearity. So here's just a fun little symmetry problem I made up. So let x, y, z, this is just good practice with linearity and symmetry and what does IID actually mean, things like that. So let's let x, y, and z be IID positive random variables. And the problem is find the expected value of x over x plus y plus z. Okay? Now, you can't do linearity on a quotient. You can't just say that this is e of the top over e of the bottom or anything like that. That's not linearity. You can't do things like that. Linearity is for sums. Okay, so at first this looks like kind of a mysterious problem maybe, in that we haven't really dealt much with quotients of random variables, and I didn't give you any explicit formula for the CDF or the PDF. I didn't say if they're discrete or continuous. I just said they're IID positive random variables. I only said they're positive just so that we don't have to worry about dividing by 0, okay? No other assumption, so this is very general, okay? So to solve this, we just need to see the symmetry of the problem. The symmetry is that we have 3 IID random variables, okay? And we took one of them divided by the sum of all 3 of them. But by symmetry, that has to be the same as e of y over x plus y plus z, right? Because I could have listed these in a different order and it would have been the same problem, right? It's completely symmetrical because they're IID. So, I mean, maybe I should have written y plus x plus z, but that's the same thing, right? It doesn't matter what order you add them in. So that's the exact same thing, but by symmetry, similarly, that's the exact same thing as e of z over x plus y plus z. So whatever this quantity is, it doesn't matter which way we write it because they're IID. I'm not saying x equals y. I'm just saying this problem, if I'd asked you this problem, that has the same structure as this problem, has the same structure as this problem, they must be the same thing by symmetry. So these 2 steps are by symmetry. Okay, well now, I have these 3 different expectations, and that makes me think of adding them and using linearity. So what if we added these three things? So if we added them, that would be e of x over x plus y plus z plus y over y, e of y over x plus y plus z plus e of z over x plus y plus z. Oops. X over, this is z over x plus y plus z. And then use linearity. By linearity, that's just e of x plus y plus z over x plus y plus z. Okay, now that's a very easy problem. Expected value of 1 is 1. But on the other hand, this is the same thing added 3 times. So 3 times this thing is 1. So that tells us that the thing we want is 1/3. So it's basically immediate by symmetry and linearity. And I think intuitively, this seems like a very kind of general thing, and like how did that always work? But if you think about this, that's a pretty intuitive answer. Like that would have been a good guess. If you had done this and gotten like 4 as your answer, you should immediately know that would be wrong, because the denominator, it's a number between 0 and 1, right? The denominator is bigger than the numerator. I said they're positive. So it has to be something between 0 and 1. 1/3 makes sense, because if I asked you just intuitively, we have 3 things, and how much would you guess that one thing contributes to the total? 1 out of 3 things, you would guess 1/3. So it's a pretty intuitive answer. But that's not a proof, and this is a proof. Okay, so that's just an example of symmetry, linearity, that stuff. Another thing we should talk a little more about is Lotus, because Lotus is something that looks very, very simple, but students make mistakes a lot with it. So here's a simple Lotus example that I made up. So here's the problem. The problem is, let u be uniform 0, 1, and let x equal u squared, and let y equal e to the x. Is that what I want? Yeah, e to the x. And and the problem is to find the expected value of y as an integral. In general, like on the midterm, I'll be very clear about, like, if you might have a hard integral that you wouldn't have to do. I would say leave it as an integral in that case. Or if it's stated that you should actually compute the thing, so I'll say whether it should be left as a sum or an integral, or if it doesn't say leave it as an integral, then you should get an actual number and fully simplify everything. Okay, so in this case, suppose I said find this as an integral. Well, it's clearly a Lotus problem, and there's 2 approaches you could take, but a lot of students in previous years have kind of mixed up the different approaches, and it's kind of for an interesting reason that I wanted to tell you about. So one approach would be to say e of y, so we want expected value of y. Well, that just looks like an easy Lotus problem, right? So e of y equals, Lotus says we integrate, we'll just change capital X to lowercase x. So we go e to the x times the PDF of x, f of x dx. And we need the limits of integration for x. So u is between 0 and 1, so x is also 0 to 1, because you're squaring a number between 0 and 1. So you get that. So I mean, this is correct, where this is the PDF of x. I mean, this is true, but this would not, this is not a full answer, because you haven't said what's f of x. I haven't said what's f of x. I mean, I said it's the PDF of x, but what's the PDF of x? Right? So if I say write it as an integral, it should be like an actual, integral, where you're saying what you're integrating. Here we just said that's the PDF. What's the PDF? Okay? So at this point, you could find the CDF of x, and then take the derivative and get the PDF. that's similar to the problem you just had on the homework. Slightly easier here. You had the homework problem uniform between -1 and 1. Okay. This is a little bit easier because you don't have to deal with negative numbers. So you could find the CDF and then find the PDF and plug that in, and and that would be perfectly valid. But that would be more work versus doing it the better way. The better way is to think of it, y equals e to the x is a function of x, but x in turn is a function of u. So I could also write this as e to the u squared and do Lotus this way. So if I did it this way, then I would just say it's the integral 0 to 1 e to the u squared du, because we know that the PDF of u is just 1 on this interval. So if I did it this way, I could write down the answer in like 1 minute, right? This way, then you have to do a separate calculation. Now, I mean I'm saying better just for like writing down the integral immediately. Not necessarily better for solving the integral. If we want to get a number, then that kind of looks like the Gaussian integral again, except without a minus there. And okay, but the problem just says leave it as an integral. Then this I could just write down instantly, right? And here we have to first find the PDF. Both of these are correct, though, so you get full credit either way, as long as, if you did either of these, as long as you actually worked out explicitly what the PDF is, that's perfectly fine. Where you'd run into trouble, though, like a lot of students had trouble in this kind of thing, was somehow like mixing and matching these two things. Like somehow I think there's a mindset that just because we defined Lotus and we called our random variable x and we looked at functions of x, that somehow it depends on x. And then if we had another Lotus problem where I don't even mention x, and then there's going to be a lot of answers where x's appear. Well, what's x, right? So the important thing is the pattern, not what you call the variables. Okay. Anyway, that's just some comments about Lotus. Other questions on anything? Yep. Yeah. How would you find the PDF? Yeah, so let's do that as quick practice with not only with PDFs, but with CDFs. Okay, so first find the CDF. So the CDF is the probability that u squared is less than or equal to some number x. That's x, but I'm trying to reduce it back to u. So the CDF would be this, and as I said, it's kind of similar to your homework, but easier, because here we don't have to worry about negative numbers. So I just take the square root of both sides. That's just the square root of x if x is between 0 and 1. That's the CDF. The derivative is the PDF is just going to be 1/2 x to the minus 1/2. Again, x is between 0 and 1. So get the CDF, take the derivative, and get the PDF. To get the CDF, all we have to really do is understand what a CDF is, and then reduce it back to the uniform, which is something we understand. Okay, other questions? Okay. So I want to do a quick example of a story type of proof, just to review that a little bit. This is a very simple one, but I think it's interesting. Just as quick practice, right? So quick story practice. If we let x be binomial NP, and the problem is find the distribution of n minus x. Well, one way to do it, this is quick practice with Pmfs, would be, n minus x is discrete, let's find its Pmf. Well, its Pmf is the probability that n minus x is some number k, but let's just rewrite that as the probability that x is n minus k. Those are the same events. Now we've reduced it back to x. Probability that x equals n minus k, that's just from the binomial Pmf, n choose n minus k, p to the n minus k, q is 1 minus p again, q to the k, right? So that was easy, but a nicer way to write that would be n choose k, q to the k, p to the n minus k. So that would be the Pmf method. Remember that n choose n minus k is n choose k, which you can prove easily either using factorials or just by the story. Picking k is the same as picking n minus k. Okay? But a simpler way, not that this is difficult, but an even easier way to see this is using the story. We can immediately say that n minus x is binomial nq, just by interchanging successes and failures. Okay, so the story is that x is the number of successes in n IID Bernoulli P trials. So x is the number of successes, then obviously n minus x is the number of failures. Okay? But we said repeatedly that you can define success and failure however you want as long as each trial is either success or failure but not both. So if we redefine success to be failure and redefine failure to be success, then that's immediate. So I'll just call that swapping success and failure. Because you define it however you want, right? So we could redefine it the other way around, and then that's immediate. So no calculation whatsoever, just one line, just swap success and failure. That's it. So swap success and failure, and I hope that none of you have to do that on the exam, but I think it's good practice. Now, okay. So we haven't done any Poissons yet today. So there's a Poisson example that I think is also good practice. Question? Yeah, the question is whether on the midterm there may be questions where you can just write things down in one line. And yeah, there's a good chance that you'd have to write something, right? But there may be several things where you just write like one line or one sentence of explanation because you see the story or the pattern or the structure, right? Like one sentence of what's going on, like this. I mean, this would be just writing this immediately, then it doesn't say how you got there. But by saying we're interswapping success and failure, that's a sentence, and there's a good chance of something like that, which would save you some time. So that's part of the point. Yeah. Oh, you get extra credit for writing it's immediately obvious? Yeah, well, don't waste time writing it as immediately obvious. You got to conserve time. Time is precious. Yeah. So let's do a Poisson problem. So here's the problem. Suppose that the number of, this is just an example that I like. Suppose that the number of emails that I get in a time interval of length t, let's just say time t, is distributed as Poisson of lambda t, where lambda is some constant. So we're thinking of lambda as a rate times time, right? So if I get, if I get, say, 20 emails per hour times the number of hours, then that would be the expected number of emails. Remember that this is, lambda t is both the mean and the variance of this distribution. Okay, so it's a random variable because in different intervals of length t, I'm not always going to get exactly the same number of emails, so there's some distribution to it. Okay, now the problem is find the PDF of t, which we define as the time of the first email. Like let's say right now is time 0. Starting now, what time will my first email come? So that's in continuous, right? That's a continuous time problem, right? Because the emails could arrive at any time in continuous time, whereas this is discrete because I'm counting the number of emails, okay? So So this is kind of neat because it's just connecting discrete and continuous. And let's see how to do it. So find the PDF or the CDF. Once we have the CDF, we could take the derivative. So I would normally just say find the distribution or find the PDF or the CDF. Any of those would be fine. So the CDF would be the probability that t is less than or equal to t. That's a little bit, remember, just as just general advice, when finding probabilities, you should think about, is it easier to find that probability or find the complement? In this case, if you think about it a little bit, you'll see that it's easier to find the complement. So let's find the probability that t is greater than t, little t. So that's just 1 minus the CDF. So if we have this, we know the CDF. This is a little bit easier to think about because if we imagine a timeline here, where here's time t, and if we draw an x every time we receive an email, t greater than t means that the first email, let's say it's there, so that's time capital T, is to the right of here, right? That says that from time 0 to t, you have no email, right? That's exactly what this says. It says that in time 0 to t, you have no new mail, right? It's exactly equivalent. Therefore, that's the exact same thing as saying that the probability of n, t greater than t, says that nt equals 0, where nt equals number of emails in that time interval from 0 to t. So I'm defining n sub t to be the number of emails in this time interval, 0 to t, but t greater than t says there are none, right? It's the exact same thing. And we assumed that this is Poisson lambda t. So this thing, just using the Poisson Pmf, is e to the minus lambda t to the 0 over 0 factorial, but that's just e to the minus lambda t, right? So the CDF is 1 minus that. 1 minus e to the minus lambda t for t greater than 0. And if we want the PDF, just take the derivative. So you got lambda e to the minus lambda t. Okay? So that's connecting the Poisson, counting number of emails to this is called the exponential distribution, again related to a homework problem, and again we'll talk about this distribution later. You don't need to know the exponential distribution yet, but it'd be reasonable, to be able to do a problem like this where we're just using the Poisson, which is discrete, to get a PDF. Lastly, I just want to remind you again, be very careful about the difference between we sort of have three classes of objects. We have our distributions. The distribution is the blueprint for creating a random variable. That was our random house. And then don't confuse a random variable with a constant. A constant would be like a specific house. The random variable is the random house. The distribution, the CDF, is the blueprint. And so mixing up those things causes a lot of trouble, so be very careful about that. All right, so good luck.